Hi everyone, my name is Monica Shaker. I'm an AMS and math major at Swords University, also sophomore.
Hi, I'm Kaylee Clark. I'm a senior at Mount Holyoke College, and I'm double majoring in computer science.
And we are presenting a model for the payment of ecosystem services, also a WCS model. It's the same thing. So our problem.
Deforestation driven by industrial soybean cultivation has significantly impacted communities and ecosystems in Argentina, especially in regions like the Cerrado and Chaco forest. Our goal is to develop a Markov model that evaluates the effectiveness of market-based strategies aimed at halting deforestation in the context of volatile industrial agriculture.
And our approach is that we utilize a discrete time Markov model to understand the underlying drivers of the deforestation process and ways to combat forest loss using the payment for ecosystem services, also known as PES. And in the context of large-scale agriculture, our focus for the Markov model is to explore how commodity price variability affects deforestation. We model these using price fluctuations as geometric Brownian motion, also known as geometric Brownian process.
So, what is geometric Brownian process or progression? Here in our model, we describe it as the equation for dV. Geometric Brownian motion has two distinct parts in our equation. It has our deterministic and our stochastic. In our stochastic, we have a special property with dBt, where Bt is a Brownian process, where it shows that the value over time follows a normal distribution. Also, we've taken a property from our original equation, where it says the expected value of v sub t plus I given v sub t equals v sub t e to the ui.
Okay, so our one-step transition matrix. This matrix represents the probability of transition between a forested parcel of land to a deforested parcel of land. And we note that with the letters here, F and D. So here, this is a forested parcel of land that stays deforested, a forested parcel of land that transitions to a deforested parcel of land, a deforested parcel of land that transitions to a forested parcel of land, and the probability of transition from a deforested parcel of land that stays deforested. And to note, we want to note the parameters that are important to our probability of transition. So this is the parameter for the probability of transition from a forested parcel of land to a deforested parcel of land at time t, where we have this piecewise function, which is lambda 1 times the expected value of the present value of a forested parcel of land at time t with this condition and 0 otherwise. And then we also note the parameter important to the probability of transition from a deforested parcel of land to a forested parcel of land at time t, noted by this piecewise function, which is lambda 2 times the expected value of negative the present value of a deforested parcel of land at time t with these conditions and 0 otherwise.
And so for the forested present value, our equation is represented by the negation of the initial cost plus the summation of revenue at time I minus the expense at time I, all of the depreciation. And we'd like for you to note that the forested present value is a rate variable. And so in order to find the expected value, we expand the equation with again the negation of the initial cost minus the expense at time I plus the revenue at time I. And since the expectation of a constant, which expense at time I is, it's just the constant itself, leaving us with the first negation of the first constant, plus the expectation of whatever is left. And since the expectation of the constant is the constant itself, we are left with the expectation of v at time I over depreciation. And as Keely noted earlier, v at time t is the equation v at time t times v to ui, leaving us with another geometric series. And when the geometric series converges, we're left with another constant, leaving us with the negation of the initial cost minus the first constant plus v at time t times the second constant. And the expectation for deforested parcel of land has a similar process, only just taking out the initial cost, leaving us with the negation of the first constant, our ongoing cost, plus v at time t times the second constant.
So, now that we found our equation and some more parameters, now we need to find out what v of t is. So, v of t in our equation, in our model, we've defined it as the price of soy at time t. So, we don't exactly know what the market could do, based on current events and stuff like that. So, we don't exactly know what t would be. be, but we can approximate. So we approximated using Euler's method. Euler's method is a mathematical technique used to approximate ordinary differential equations, and we use it in our model to approximate our stochastic differential equation. So here's an example from Google Summer, where we have our original function, like that function, and then we have our initial point. So then we use our stochastic differential equation to calculate the slope in by small increments of steps to reach to another point and continue on until we follow the whole original function. So here you can see that from A0 all the way to A4, we try to get as close as possible to the original.
And so in order to find the parameters for our model, we use the geometric rounding process that we mentioned earlier. And the dB over B has a normal distribution with the mean of UDT and a standard deviation of C times the square root of UT, or the square root of C times T. And since dB is just such a small difference between the number of days, it can be compared to the closing price from one day minus the closing price of the day before, and B as the closing price of the day before. And so this difference quotient is what we use to find the parameters. And as you can see towards the end, our points kind of skew like off the line, not really fitting the normal distribution. So we performed an outlier analysis to make sure that the points fit the normal distribution better. And this proves that our model is a good model to use, as well as our histogram that our points in the box plot that are the first program to earlier, as well as it fits the normal distribution overlay, and it proves that our geometric rounding motion is a good model to use.
So now that we have our equation, our parameters, and now we know that our model is good enough to simulate, we ran some simulations using Python, where here you'll see the soybean prices over the course of 5 years, like predicted in the market, and each individual spike here is a run. We have 10,000 runs, and these lines here represent the mean. We have the 5th percentile and the 95th percentile. And over here is kind of our parameters and numbers we chose to construct our simulation. So we have U, where it equals the negative 0.025, Z 0.200, our first constant or our constant initial equals 1, our second constant equals 2, and lambda 1 and lambda 2 equals 0.3. When we chose lambda could be any number, but we chose 0.3 because that's how we thought the market would fluctuate. And I'd also like to note that our mean came in 0.002 of our parameters, so it's very close to each other.
So now what? Now that we have proposed a model for soybean prices, we have validated and found parameters from data, and we have calculated the mean and coefficient intervals for soybeans. What does this mean for deforestation? So we'd like to know that our transition matrix, given our expected value of V of t, is equal to e to the negative 0.035t, and our transition matrix with this expected value is expected to be the identity matrix, where we expect a forested parcel of land stays forested and a deforested parcel of land stays deforested. But
in our findings, we find that if we do include stochasticity or price variability, we find that instead of the identity matrix where a forested parcel of land doesn't transition to deforested, we actually found that instead of 0, it's 15%. So if you think about that, where we're actually in the real world, we're expecting that forested parcels of land stay forested, but they're actually going to become deforested.
And here we also have a graph with the averages, the average probability of transition over lambda, where lambda represents the activity in the market. So as the market gets more active, so too does the probability of transition, the average probability of transition from a forested parcel of land to deforested, and the probability of a deforested parcel of land becoming forested also starts to increase, but much less than the probability of transition from a forested parcel of land to deforested. So the effect of PES, or payment for ecosystem services. Now that we've created a model without PES, we want to introduce payment for ecosystem services, or PES, and examine how it affects the present value of and using 3 different PES programs. We will use relative risk to understand how PES impacts present value.
And so the three PES programs we're going to be using, one is fine, and since fines only affect the initial cost, it's only present in the expectation of the forested parcel of land and not present in the expectation of the forested parcel of land. And for flat rate, because it affects the ongoing cost, the first constant, it affects both the expectation of forested parcel of land and the expectation of deforested parcel of land. And market-based affects the revenue at time t, so it both affects the expectation of forested parcel of land and deforested parcel of land.
So, relative risk. Relative risk we can define in our study as the average probability of transition with policy over the average probability of transition without policy. And with this ratio, we want to note that if relative risk is approximately 1, then there is no effect on what we want. If relative risk is much less than 1, then the policy has a minimizing effect, and if relative risk is much greater than 1, then it has a maximizing effect.
So now that we have our model of TOE and now we have our TPS also with our relative risk, here is all the data points that we have, but in order to give more sense, words, what is the actual effect of PES programs? So here I'd like to know that if a government or a policymaker was considering, oh, what should I do to alleviate poverty? We found that the best programs would be subsidies, so either flat rate or market-based. They have a mitigating effect on poverty. For deforestation prevention, it would be either market-based fees or subsidies, has a large protective effect. And reforestation incentive